Hello everyone, this is the group literature review for the project Real-Time Collision-Free Navigation of Multiple Autonomous Vehicles. So let's begin with the overview. We first reviewed the paper for collision-free navigation of autonomous vehicles. This provided us with a clear picture of various methods and approaches to deal with autonomous vehicles in cluttered environments. And after reviewing this paper, we decided to proceed with the model predictive control and velocity obstacle method for dynamic collision avoidance. So now Fennel will be explaining more on these survey papers.
Let's talk about the paper Algorithms for Collision-Free Navigation of Mobile Robots in Complex Cluttered Environment, a survey. This paper reviews a range of techniques related to navigation of unmanned vehicles through unknown environments with obstacles, especially those that rigorously ensure collision avoidance. This topic continues to be an active area of research and highlights some direction in which available approaches may be improved. The paper discusses vehicle kinematics, assumptions about the environment, and performance criteria. Methods applicable to stationary obstacles, moving obstacles, and multiple vehicle scenario are all reviewed. In preference to global approaches based on full knowledge of the environment, particular attention is given to reactive methods based on local sensory data, with a special focus on recently proposed navigation laws based on model predictive control. Let us now talk about problem consideration. The first part is environment. Your definition of cluttered environment consists of 2 to 3 dimensional workspace which contains a set of simple closed untraversable obstacles which the vehicle is not allowed to overlap. The area outside the obstacle is considered homogeneous and equally easy to navigate. Examples of cluttered environments may include offices, man-made structures, and urban environments. An example of classification of objects in an urban environment is available. The vehicle is specially modeled as either a point, a circle, or polygon in virtually all approaches. Polygons can be conservatively bounded by a circle, so polygonal vehicle shapes are generally only used for tight maneuvering around closely packed obstacles, where an enclosing circle would exclude marginally viable trajectories. There are many types of vehicles that must operate in cluttered environments, such as ground vehicles, UAVs, surface vessels, and underwater vehicles. Most vehicles can be generally categorized into three types of kinematic models: holonomic, unicycle, and bicycle, where the differences are categorized by different kinematic constraints. The term dynamic is used to describe model based on the resolution of physical forces, while kinematics describe model based on more abstract control inputs. Holonomic kinematics. These describe vehicles that have control capability in any direction. Holonomic kinematics are encouraged as helicopters and certain types of wheeled robots equipped with omnidirectional wheels. Holonomic motion models have no motion of body orientation for the purpose of path planning, and only the Cartesian coordinates are considered. However, orientation may become a consideration when applying the resulting navigation law to real vehicles. Through this is decoupled from planning. Unicycle kinematics. This describes vehicles that are associated with a particular angular orientation which determines the direction of velocity vector. Changes to the orientation are limited by a turning rate constraint. Unicycle models can be used to describe various types of vehicles such as differential drive wheeled mobile robot and fixed wing aircraft. Bicycle model. This describes a car-like vehicle which has a steerable front wheel separated from a fixed rear wheel. Kinematically, this implies that the maximum turning rate is proportional to the vehicle's speed. This places an absolute bound on the curvature of any path the vehicle may follow, regardless of the speed. This constraint necessitates high-order planning to navigate in confined environments. There are several different methods of preferentially choosing one possible trajectory over another. Many path optimization algorithms may be implemented with various such measures or combinations of measures. Common possibilities are minimum distance. This is used in the majority of path planning schemes as it can be decoupled from the available velocity profile of the vehicle. Minimum wheel rotation. This applies to differential drive robot and in most cases in only certainly different form the minimum distance formulations. However, it may perform better in some situations, especially when fine movements are required. Minimum time. Calculating the traversal time of a part depends on the velocity profile of the vehicle and thus includes kinematics. It would be more appropriate than minimum distance for selecting the trajectory that completes task in the most efficient manner. It is often used in MPC based approaches. Minimum control effort. This may be more suitable for vehicles operating in limited energy environments. Optimal surveillance rate. In unknown environments, it may be better to select trajectories that minimizes the occluded part of the environment. In cases where occluded parts of the environment must be treated as unknown dynamic obstacles, this could allow a more efficient traversal through it, though it would be unavoidably rely on stochastic inferences about the unknown portion of the workspace. This paper also introduces model predictive control. It should be said that if an obstacle avoiding trajectory is planned offline, there are many examples of path following systems that are able to robustly follow it, even if subjected to a bounded disturbance. However, the lack of feasibility means that the environment would have to be perfectly known in advance, which is non-conducive to an online collision avoidance. MPC is increasingly being applied to vehicle navigation problems. It is useful as it combines path planning with online stability and convergence guarantees. This is basically done by performing the path planning process at every time instant. Then apply the initial control related to the chosen trajectory to the vehicle. In most cases, a partial path that terminates with an invariant vehicle state is employed, which minimizes some cost to go function corresponding to the target. By repeating this process at every time step, the controller can be shown to be stable. This paper focuses on multiple vehicle navigation also. There are three major factors here. First is communication type. There are three common modes of communication in multiple vehicle collision avoidance system. First is direct state measurement. This can be achieved using only sensor information to measure the state of the surrounding vehicles and is used in many non-path based reactive approaches. Single direction broadcasting. In addition to the physical state of the vehicles, additional variables are also transmitted, usually relating to the current trajectory of the vehicle. This is often used in mutual exclusion based path constraints where the projected states of another vehicle are avoided during planning and is occasionally referred to as a signboard communication. Two-way communication. This can range from simple acknowledgement signals to full decentralized optimization algorithms. These are commonly used for decentralized MPC, though some MPC variants have been proposed where signboards are sufficient. Reactive methods. Potential field method. Potential field methods can be constructed to repel other vehicles. In some ways, this approach is more satisfactory than the equivalent methods applied to static obstacles. For example, local minima are less of an issue in absence of contorted obstacle shapes. Methods have been proposed which avoid collision between an unlimited number of velocity controlled unicycles or velocity controlled linear vehicles. Reciprocal collision avoidance method. Approaches termed reciprocal collision avoidance achieve collision avoidance by assuming that each vehicle takes some responsibility of each pairwise conflict, with the resulting constraint forming a set of viable velocities from which a selection can be made using linear programming. Some interesting extinctions have been proposed to the ORCA concept. For example, it has been applied to both non-holonomic vehicles and linear vehicles with acceleration constraints while maintaining collision avoidance. Hybrid logic approaches. For these approaches, discrete logic rules are used to coordinate vehicles. In most cases, this is achieved through segregation of the workspace into cells, which can each only hold one vehicle. Last part is decentralized MPC. Decentralized variants of MPC is generally do not specifically address the problem of deadlock. A distributed navigation system is proposed, which is able to plan near optimal solution, then robustly prevent collisions, and allow altruistic behavior between the vehicles that monotonically decrease the global cost function. However, this does not equate to deadlock avoidance, which can currently only be solved in general using discrete graph-based methods. This is a table presented in the paper that compares MPC, DMPC, boundary following, velocity obstacles, and other methods according to their utilities for single vehicle, moving obstacles, multi-vehicle, and boundary following approaches. And here are some of the keys that are mentioned below in this slide. Some of the open research questions that appear after reading this paper are: first, can directly applying neural network fuzzy logic or iterative learning based approaches to vehicles guarantee motion safety? Can sensor-based planning approaches be applied to autonomous vehicles? And how well biologically inspired planning can perform in multi-agent navigation? Let's talk about the paper Non-Holonomic Mobile Robots Trajectory Tracking Model Predictive Control, a survey. According to Brocket theorem, a smooth, time-invariant static state feedback control law cannot be used to stabilize a non-holonomic system at a given configuration. In the last 10-20 years, MPC theory has been trying to solve this control problem. MPC aims to solve optimization problems using a prediction horizon of the system's behavior with input and state constraints. A major concern in the use of prediction horizon is to determine whether such an open loop control can guarantee system stability. It is shown that an infinite prediction horizon can guarantee stability of a system, but the choice of infinite prediction horizon may not be feasible for nonlinear system in practice. The term MPC, also known as receding prediction control (RHPC), does not designate a specific controller but rather an ample range of control methods that make explicit use of model of the process to obtain the control signal by minimizing the cost function. The most important concepts appearing in the predictive control family are basically: first, explicit use of model to predict the process output at future time instants; second, calculation of a control sequence minimizing a cost function; and third, receding strategy, so that at each instance the horizon is displayed towards the future. The MPC problem is formulated as solving online a finite horizon open loop optimal control problem subject to system dynamics and constraints involving states and controls. Based on the model of and measurements obtained at time t, the controller predicts the future dynamic behavior of the system over a prediction horizon of Tp and determines over a control horizon of Tc, that is less than the prediction horizon, the input that a predefined open loop performance objective function is optimized. If there are no disturbances and no model plant mismatch, and if the optimization problem can be solved for infinite horizons, then one can apply the input function found at time t equal to 0 to the system for time t greater than 0. However, notice that this is not possible in general. Due to disturbances and model plant mismatch, the true system behavior is different from the predictive behavior. In order to incorporate some feedback mechanism, the obtained open loop manipulated input function is implemented only until the next measurement becomes available. The time difference between the recalculation can vary. However, it is often assumed as fixed. The measurement takes every delta sampling time units. Using the new measurement at time t plus delta, the whole procedure, prediction and optimization, is repeated in order to find a new input function with the control and prediction horizon moving forward. There are two major types of MPC, linear MPC and non-linear MPC. Let's talk about linear MPC. Non-holonomic systems are naturally non-linear. In order to control such a system using a linear controller, one must linearize the model first. Early research works on this subject use prediction models derived from linearized tracking error dynamics to predict future system behaviors. A control law is derived from quadratic cost function involving system tracking error and control effort, including velocity and acceleration constraint to prevent robot from slipping. When using low processing embedded systems, a local approach of linear MPC can be used despite the large tracking error. Mobile obstacles avoidance can also be included in the cost function by maximizing the distance between the robot and static obstacles. Also, saturation of the actuators can be considered in linear MPC approach. Now, non-linear MPC. Since linear MPC is not feasible for mechanical benchmark problem, the potential of non-linear MPC technique is investigated over the years. Nonlinear MPC implementation demonstrates that the cost and reliability of non-convex optimization are critical issues, making the tuning of controller parameters to be decisive. In general, terminal state constraints are required to guarantee asymptotic stability. Let's focus on the nonlinear MPC model in detail. The minimization by the optimizer and the predicted behavior are the main blocks of the MPC theory. When applied to solve the trajectory tracking control problem, the nonlinear MPC gains a new subpart, being thus divided into three subparts. Path generator. This subblock receives the global trajectory calculated by a trajectory generator and creates a reference signal to be followed by the controller using the prediction horizon. Optimizer. This subblock uses an online numeric minimization method to optimize the cost function and generate the signal of optimal control. In MPC algorithms applied to mobile robotics, it usually uses the gradient descent algorithm. Predictor. The predictor computes the predicted state evolution of the robot itself. It uses a simplified robot model to emulate the robot evolution and calculate the final value of the cost function. Now let us discuss about the NMPC example using differential drive robot that is presented in the paper. The relevant variables for kinematic model of a typical two-wheel differential drive mobile robot are its center position coordinates, that is XR and YR, its angle of orientation, that is theta R, along with its linear and angular velocity VR and omega R respectively. The classical prediction model that is described in equation 1, the constraints shown in equation 2 must be respected in order to avoid lateral slipping from the wheels. Finally, we can perceive the error states X, E, Y, E and theta E used to predict the robot's movement error, which are selected in the rotated coordinate frame as seen in equation 3, where a desired reference trajectory is defined by a reference state vector xref. Now, the relation between linear and angular velocity v and omega with the wheel motion. The relation between the angular velocity of each wheel and the robot's linear and angular velocity is shown in equation 4 over here, where omega 1 and omega 2 are the angular velocity of the right and left wheels, respectively. R is the vehicle radius and D is the length of robot's base. By combining equation 1 and 4, we can obtain a model that expresses robot's coordinates and orientation in terms of the angular velocity and its wheels, as shown in equation 5 over here. Also, equation 4 can be easily manipulated to show the direct relation between the control output to the desired trajectory and the input, the right and the left wheels angular velocity, as shown in this equation 6. The cost to be minimized by the predictive controller is typically associated to the dynamical change of the system over time. In the trajectory tracking problem, the cost function must penalize the difference between the pose of the robot and the pose of reference given by the trajectory generator. Additionally, the cost function has a term that penalizes the control effort. Each of these penalizations is associated to a weight that defines the proportion of penalization over the global value of the cost function. The cost function that has to be minimized to the control trajectory of the non-holonomic mobile robot is in general given by this equation 7, where N1 and NP are the prediction horizons limit in discrete time and NC is the control horizon. Lambda 1, lambda 2 and lambda 3 are the weights. This simulation just illustrates the application of NMPC controller in differential drive mobile robot subjected to non-holonomicity and noise. Here the robots travel in a straight line, whereas here the robot follows a circular trajectory. Here we can see this is a summary table of different optimization methods that is useful for model predictive control implementation that are presented in the paper. Here we can also see that some of the methods have not been implemented in experiments. Here in this table, we can observe the comparison between different predictor model methods. Here we also see that model types are linear, non-linear and linearized, and some of them are also not presented in experiments and are open to research. Some of the open research questions that we came across after reading this paper were: can absence of formal guarantee over the finite planning horizon of nonlinear MPC be compensated by rapid open loop optimization for real-time optimal response? Second is, how well MPC based method will perform with probabilistic localization of vehicles and imperfect sensing of the dynamic obstacles? Does better approaches than steepest descent exist for solving online optimization for MPC? Can learning based approaches like CNN RNN be used for online model estimation while using MPC?
Thank you, Fanal, for the great explanation. So now let's dive deep into the velocity obstacle methods. Our main purpose of performing velocity obstacle analysis is to ensure that we do not collide with high-speed vehicles that are moving in the environment. We'll be focusing on mainly 4 methods that include generalized velocity obstacle, reciprocal velocity obstacle, optimal reciprocal collision avoidance, and acceleration velocity obstacle. The first paper here we're going to look is the generalized velocity obstacle. In this, the author tackles the issue of dynamic collision avoidance for car. So here the problem, let's understand the problem description. The goal here is to define a velocity obstacle that is basically the set of velocity inputs that would lead to a collision. Next, it is to generalize this concept of velocity obstacle and extend it to non-holonomic robots. So let's understand the proposed method. First, here we have the robot A and the obstacle B. What we do is we inflate the by using Minkowski's sum, and that is this gray region which we see here. Now we would join the point A to the obstacle B to form this cone, and then shift it to VB by VB velocity. So here what we see, the pink portion, is our velocity obstacle. Alternatively, we can say that the VA minus VB relative velocity should not lie in this cone, or the VA velocity should not lie in this pink area. But the time where minimum distance would occur is given follows. So using this minimum time, what this says is that at this time, the obstacle B and the robot A would be the closest possible. And now using this, we can find the it should be less than RA plus RB. And if it is less than RA plus RB, that means the robot is going to collide. Here let's understand it for the non-holonomic robot. Here we consider the bicycle model, and we can observe that the system is fairly complex to solve. So like while integrating, we find that the position vector looks something like this, and the minimum time which we found for holonomic case, here non-holonomic, it's not a simple solution, and hence we decided to do this solution iteratively. So basically we select a set of input velocities and check if these velocities would collide, and then check if this velocity is more closer to the current velocity. And by this, we get to know after a range of velocities that this is the best velocity we can apply. And in this manner, we get the desired control input. So based on this, the authors did some experiments. Here we can observe that first experiment is on processing time and agent time with varying the number of obstacles. So as we increase the obstacles, here at around 15 obstacles, stops being in real time. So the processor time is more than the agent time. Also, if we increase the number of samples, then the agent becomes faster. But at 40 samples, the simulation stops being again in real time. And if we vary the time step length, the time between which new samples are taken and a control is selected, the top graph shows that between 0.1 and 0.3 seconds, real-time processing becomes possible. And also we can observe the success rate for each. So as we increase the number of obstacles, the success rate decreases. And increasing the number of samples initially decreases, and then this is the success rate of the problem. And similar case for varied time steps, the graph shows that on increasing the time steps, we decrease the success rate. This paper immensely contributes in generalizing the velocity obstacle and in applying this concept to a car-like robot. It also allows a wide range of inputs to choose from. However, the questions are as follows. It uses a numerical means to calculate the minimum distance. Therefore, it's a probabilistic algorithm. Hence, the solution may not be found. Also, there is some inaccuracy in the computation of distance, hence the small buffer here is necessary. Also, this control method which they have used in the paper is a very greedy control method. Hence, the robot can easily get stuck in a local minima. And most importantly, the acceleration constraints are not considered. Hence, basically, the robot can instantaneously change its velocity at a given time. So now let's look into the second paper, that is reciprocal velocity obstacle for real-time multi-agent navigation. Here, basically, the paper is using the concept of reactive nature of the other robot as well. So let's understand in more detail. So in this method, author tackles the issue of dynamic collision avoidance for multiple car-like robots. So here we assume that the opposite obstacle is also a car and it's reacting in a similar way. So what happens is if we use the normal velocity obstacle, this robot would react this way and this would react in that way, and hence again it would reach the same condition where it's going to have a collision in next time t. So it again moves in the straight direction, then again changes. So this is the oscillating nature that we observe. And to tackle this, the author considers the reactive behavior of other agents that was not considered by the velocity obstacle in the first place. Also, the author demonstrates that this scalability can be done in real-time and challenging scenarios. The proposed method is similar to the velocity obstacle. The major difference is that instead of a velocity that we pick out, viewer, they rather average the current and the velocity of the other agent outside the viewer. So here basically you're shifting the apex by VA plus VB by 2 of velocity obstacle. They perform various experiments. So initially they place a few amount of robots in a circle and make them go to opposite directions. So here we can observe that in case of a normal VO, we see these haphazard motions. So these are the oscillating nature which we are talking. But in case of reciprocal velocity obstacle, the trajectories are smooth. Second experiment which they performed was on a moving obstacle. So here this gray is box is the car, and this is the people moving in a straight line. So they're trying to go from the left to the right, and we can see how it is avoiding the car as well. And here the car is considered to be a high-speed obstacle. Then also this is a narrow passage through which we are like diagonally making the robots up to the opposite point. So the yellow one goes here and the blue one goes there, green one goes here, and the red one comes back here. So here we see that some of the agents, as the number of agents increases, some of them get stuck. Later they come to the desired position eventually, but this is some limitation of the method that it is not at most optimal. And that this optimality is then tackled in the next paper, which we'll be looking in some time. The reciprocal velocity obstacle paper contributes immensely in formulating the reciprocal velocity obstacle, and the algorithm computes smooth and natural paths for over 1,000 agents, and the oscillatory motion is effectively avoided. However, the limitations that come are high computation for higher number of agents. Avio doesn't perform fairly well for a complex and a densely packed environment that we just saw in the previous experiment. And the paper also does not consider the implementation for a 3D space. So let's jump into the next paper regarding the optimal reciprocal collision avoidance or n-body collision avoidance. And this majorly tackles the issue of the optimality of the reciprocal collision avoidance. So majorly in this paper, the author tackles the issue of n-body collision avoidance, and it is an extension of the reciprocal collision. To tackle this, the paper first defines a velocity obstacle as a truncated cone. So in other words, if at time t, this is the circle that it forms, then if we have to look for till time tau, so that is this cone. So they keep making circle, circle, and this is the truncated cone they form. So this is a different calculating the velocity obstacle that we learned. And now let's say the VB velocity has a set of velocities capital VB, and hence we can form the velocity obstacle for that as shown in this figure. So here's the VB range, and this forms the truncated cone here, and this end would form the truncated cone here. So this entire gray region would be our velocity obstacle, and outside that would be our velocities that are going to be avoiding these. So in other words, if VA is a subset of this collision avoidance versus B, and VB is the subset of its collision avoidance with A, then they are reciprocally collision avoiding. And also, if they are equal to these subsets completely, then they are reciprocally maximal as well. So once we have these set of velocities, then we need to find within this the pair that is closest to our optimization velocities. Now the selection of optimization velocities could either be 0, the preferred velocity, or the current velocity of the object. Our goal is to find now the minimum input, control input, that could be a velocity, which will help us escape the VO. And the optimal way would be to take the normal along it and some distance from it called u. And this will create some half planes in our diagram. And this is the case for a simple one-to-one robot and obstacle problem. But if we have an n-body collision avoidance, we would get several of these half planes. So we need to find a common intersection of them, and those will be the valid velocities that will prevent collision in the future time t. Now, for this this to work, we need to select an optimization velocity, and based on what we select, the answer starts differing. So if we would select a 0, we guarantee that there would at least be some velocity in the subset. So here is that example, the third figure here. It shows that this is the intersection region, hence we can select 0 as the velocity. But one issue which you can observe here is that if we start selecting 0 as our velocities, what would happen is that this would cause a deadlock in the future, and that is not desirable. So another option is to select a preferred velocity, which we might have defined at the start. So the robot would assume that the robot's preferred velocity is same as his preferred, and that would be the case in general. Like for normal cars, it is like 60 kilometers per hour. So that is some desired preferred velocity which we can take in assumption. But what happens is that when the population is too high and it's too much traffic, there's too much traffic. This is a dangerous way to work, and this is a very high velocity. Hence, this is not the best option to do. So what we can do is we can select the V optimal as the current velocity, and this is the best trade-off between both. And in case of a static obstacle, we can just assume that the velocity is 0. Now, with scalability, they perform various experiments. So the photo which we see here is a simulation of 1,000 agents moving towards the center and moving to their opposite ends. And and another test that was performed was they placed an emergency escape in the office where the agents were supposed to leave the room immediately. And they plotted this for like 5,000 agents on an 8-core processor. And you can see that it takes 125 frames per second to solve this program. And that's pretty good. So the paper contributes in the formulating an efficient method. It also exhibits a faster runtime and a smoother behavior than the normal RVO formulation, and hence it effectively replaces the initial RVO formulation. However, the limitations are that the ORCA doesn't consider acceleration constraints again, so it's just assuming that we can instantaneously change our velocity at any time t. And also the paper has not considered any scenario for 3D environments. And also the implementation shown in the paper was only for holonomic robots. So again, for non-holonomic robots, the computation time has increased, and also the solution is iterative. And now let's move on to our final paper, that is considering the acceleration velocity constraint. And this paper is called Reciprocal Collision Avoidance with Acceleration Velocity Obstacles. In this paper, the author tackles the issue of an instantaneous change of velocity and extends it to an optimal reciprocal collision avoidance. To tackle this, the paper first defines a proportional controller for acceleration to enable smooth transition of velocity, and then they solve the differential equation above, which gives them the velocity of A, and integrating them gives the position of the A robot. And similar thing can be done for the B robot. And now considering that we want to find the relative velocities that would lead to a collision at time t, we formulate this below formula. And this concept can be easily extended to n-body and reciprocal collision avoidance as shown in the previous papers. Based on this formulation, they perform various experiments, and the two interesting ones will be shown here. First is that they take n robots in a circle, and one can observe that they achieve a simulation rate of around 30 FPS for 1,000 robots. And for car-like robot, that's non-holonomic constraint, they observed smooth trajectories for random initial and random goal configurations, and the robot successfully obeyed the kinematic and dynamic constraints. So this paper helps in formulating an efficient method of acceleration velocity obstacle and extends this to the reciprocal collision avoidance. It works efficiently for non-holonomic robots as well. However, the limitations are that a much more computation time is required when compared to the optimal reciprocal collision avoidance, which we learned before this. Even though it is efficient, the paper has no 3D environments, and the possibility of inevitable collision state is not considered. So what if there is no set of velocities that would help us escape this collision? So that kind of state is not considered in this paper as well. So as we have looked at different methods for velocity obstacle, now let's have a comparison between them. So here we can observe that the green represents the things that it can do, so the pros, and the red is what is the con. So as we can see, all of them can perform high-speed obstacle avoidance. Also, only RVO, RC, and AVO can take into consideration the reactive behavior. And for complex environments, we have the ORC and AVO, while only AVO is able to consider the acceleration constraint. However, all of these papers do not consider 3D space collision avoidance, which would be an important factor for manipulation. And also, for non-holonomic robot, no one has given an analytical solution. So they mainly focus on solving this iteratively. That is, you would need to have a set of velocities which you want to choose from. So having understood these four papers, let's try to understand the different research questions we have in mind. Uh, First one being, for non-holonomic robot, they have all considered the solution to be numerical. So it's all iterative methods. So is it possible to solve it analytically? And if yes, then that would be really helpful. Also, will the implementation be easily extendable to a 3D space path planning problem that is considering the manipulation scenario? Uh, and also how to implement these paths with smoother acceleration profiles for drones. So in case of drones, we need to take in consideration jerk. So can we extend the concept of AVO to jerk as well? And how advantageous is ORCA over the acceleration velocity obstacle in terms of computation time? Because we see that AVO can avoid obstacles in a more smooth manner, but also the computation time is higher. So how much advantages is ORCA over AVO in that scenario? So that's it from the literature paper review. Thank you for following us all along, and I hope you got to learn something today. Thank you.